Hello class. So this will be your first online class. Before the break, we completed up to lesson 27. So from today, we'll start lesson 28. So it has two parts. So I will split the total video into two parts. So this is the first half. And the learning objective for this part is calculation of water surface profile for gradually varied flow using a direct step method. Before the break, we started the gradually varied flow. Just to do a very quick review, gradually varied flow was a flow where all the flow parameters with respect to distance change very slowly, which is almost zero, but not zero. And we discussed some of the basic parameters of gradually varied flow, and we stopped before the computation of water surface profile for gradually varied flow. We know there were four available methods for computation of water surface profile, and we decided that we only use the direct step method. So in this part, I will try to explain how we can actually use this method to calculate the computation of water surface profile. So you have that slides with you with all the equations and everything. If you look at the equation, the basic equation for this part is actually delta x, and all the terms like E1, E2, those are like specific energies, SV, SF are the like friction slopes and everything. We already know that. So we will use these equations while we compute the water surface profile. So the class example 19, we started, and I believe for each section, I completed part 1, but again, I'm starting from the very beginning. So the question was, a trapezoidal channel with a bottom width of 4 meter and side slopes of 1:4 carries a discharge of 30 meter cube per second. The channel has a constant bed slope, which is S naught of 0.001. A dam backs up the water to a depth of 3 meters just behind the dam. Given that critical depth is 1.22, normal depth is 1.9, and the Manning's N 0.025 and alpha 1, which is kinetic energy coefficient, you have to determine the slope type and flow type in the channel. And the main thing, you have to compute the backwater profile to a depth 5% greater than the normal depth, and finally plot the water surface profile. So that was class example 19. So at first, obviously, we'll write down what are the given values and what we have to find. So for question number 1, slope type and flow type. So from the given value, we can see normal depth is greater than the critical depth. So slope type is mild. That was the definition of mild slope. And the flow type, since the depth of water behind the dam is 3 meters, which is obviously greater than YC, and we know if the depth of flow is greater than critical flow, the flow is subcritical. So that was question number 1, and we actually completed that part. So for today's lesson, basically, we will start from the backwater profile. How can we calculate the backwater profile? And up to which point we will calculate the backwater profile? That is the question. So they mentioned you have to calculate the backwater profile up to 5% greater than normal depth. So the normal depth was 1.9, and if you add 5% extra, which will give you 1.995 meter. So just by rounding, we can consider that as 2 meters. So basically, we have to calculate the backwater profile from this 3 meter to 2 meters. So in between these two, we have to calculate the coordinate of water surface profile, okay? In using the direct step method. So all of the equations which I showed earlier, again, these are the equations. How can you calculate specific energy for section 1, section 2, and the friction slope for section 1, section 2, and finally the delta x. So that is the equation. Now we will go into the Excel so that we can do the calculation properly. And since we will do a kind of repetitive calculation, so Excel is actually very good for this purpose. So I'm moving to Excel for this one. So this is the Excel profile. I copied and pasted all the equations here so that we can look at that. That was the cross-sectional view of the channel, and that was the longitudinal view. If you can remember, the equation was actually delta x. So basically, we have to divide the sections from 3 meters to 2 meters into many subsections, and then for each subsection we will know the depth, and then for each depth we will calculate the delta x. So basically what I'm saying, in between these 3 and 2, like the whole section, we will divide into small subsection like that. Okay, and we will assume the depth of each section. So basically at first we need some depth. So what we will do, so for these, you see the y. So for the first one it was 3, the next one we can assume it's 3, 2.8, 2.6, the next one is 2.4, 2.2, 2.1, and finally the very last one is 2. And in between these two, like suppose this is the 3 meter and that is the 2.8, in between these two we have to calculate the delta x. Okay, so that's what we will do. So for delta x, if you can remember what was the equation, so let's type the equation first. What is the equation for that one? So that is the delta x, like delta E over average SF minus S naught. So we have to find delta E and this average SF and S naught. So we will work with each component separately. So at first we will calculate the delta E. So this one and the F, so that is our delta E. So for finding delta E, we need E1 and E2. So those are the two specific energy at section 1, which is 3 meter, and section 2, which is 2.8 meter. So we need the E for each section, which is y plus alpha v square over 2g. Now, we already know y, we need to know the v. So for v, what we will do, we will actually find that v square over 2g, and v equals to q over a. Q was given, so we have to calculate a. Since it's a trapezoidal channel, so E will be like a will be, we have to calculate that one, that is b plus my y. Okay, now once we know the delta E, the second term is average SF minus S naught. We already know the S naught, which is 0.001. So basically we have to find average SF. So the average SF is like average SF minus S naught, and for S naught, so average S naught is like friction slope 1 plus friction slope 2 divided by 2. So we have to calculate friction slope 1 and friction slope 2 by 2. Okay, so main thing is now we have to calculate the friction slope 1, right? Okay, so from Manning's equation, if you rearrange the whole equation, you will get this expression that n square v square over rh to the power 4 over 3 for SI system, since everything in SI system. So that is the equation you will get for SF. Now you see, we already know the V. The only thing we don't know is the hydraulic radius. So we have to find the hydraulic radius. How can we find that? You already know hydraulic radius equals to area over perimeter. Now we know the area. The next thing we need to know the perimeter. So this column will give you the perimeter. Okay. Now we have everything, delta x. Now let's write down all the unit for each parameter, so that will help us. Now if I just work with the first depth 3 meter, let's see what are the area and everything for this one. So for area is 48, V is 0.63, and we have everything. Now, since this one is the average SF, and now we have only one SF, so we don't have any average. We need to wait for the next section's SF, and then we can work on that. Okay. Now, this is the delta X. That means this one for each, like in between each section. But we want to get the cumulative delta X. So for this column, we will actually add all the delta X. Okay. So that is for 3 meter. Similarly, we can do the same calculation for 2.8, like this section. And that one is this. Now you see we have average SF, which is the average of this one and this one. Okay, so for section 3 and for section 2.8, that is the average section, and we got delta X. You may ask one question, why we are having the negative delta X. That's because flow is going from left to right in this direction, but we are calculating delta X from right to left. It's like we are going in this direction. That's why that is negative. And if we add this one, we will have, that is the cumulative delta X. Now, if I do the same calculation for every columns, so that's what I will get. And if I keep adding all of these, I will get this one. So at 2 meter depth, the distance from this column is actually 1582.85 meter. So basically now we have depth for at least 7 sections, and we know exactly what is the delta X for each section and the cumulative X. So the next part is plotting. So what you will plot, you will actually plot this Y. If I highlight that one, this one, okay, and this cumulative one, this one. So if you plot these two, I already plotted, so I can actually show you what will be that. So that will be the plotting, the depth and backward distance from the dam, and you can see that is actually a backwater water profile. Okay, so that's it for the calculation of gradually varied flow water profile. So we will move to the next part of this class. Okay.